this is the equation. In the interaction picture, we have figured out what is this V I T. So this is V is I S 0 T H cross V R of T E raised to minus I of H. So this is the perturbation in the interaction picture or the interaction Hamiltonian in the interaction picture. Clear? Yes, okay, so we have also, okay, so let's calculate. Okay, so let's work out this equation in the eigenbase of H naught. Okay, so we have at hand. So what is our problem? We are looking at a transition probability. Okay, we are trying to figure out how to calculate the transition probability. Perturbatively, a particle is making a transition from one state to the another state. Clear? If there is some external potential or external perturbation. Clear? Whether that, okay, so this perturbation is usually a time dependent perturbation. Clear? Or the interaction is time dependent interaction. Clear? Okay, so let's consider the eigenbase of this H naught. So what does that mean? I mean these are the states. Let's consider n to be the eigenstate of this with energy En. So I will not put any kind of subscript 0 here because we don't consider any correction to the energies. Okay, so it means you are having a particle in a state n, so that carries energy En. Clear? Okay, and these are orthonormal. Clear? Okay, so let's look at this equation. Okay, since this, okay, so we'll work out this equation in this basis. So we are having the basis that is formed by the unperturbed eigengets or the eigenstates of this H naught, which we know exactly. Clear? Okay, so it means I can expand any arbitrary state in terms of this n. Okay, so I will take an arbitrary state, this phi of t. Okay, so that means a time dependent state at any arbitrary time. Clear? Yes. So it's a valid justification because okay, so let me first write. So I'll write some coefficients that will depend on time and this n. State. Clear? So this is the basis extension of an arbitrary state phi. Okay, this is valid for any time t. Clear? So you take some time t and make an expansion. So why this is valid? Because this is a basis. Okay, we are not, so this some sort of, I will call this as a fixed basis. This basis does not change over a period of time. That means if you start with the eigenstates of this Hamiltonian H naught, they will always remain the eigenstates of this H naught. They do not change. Clear? So we call this sometimes as a fixed eigenbasis. So in this, okay, so we'll just see it reduces to the well-known results what we know. Clear? Okay. So what is now the thing we need to calculate? These are the unknown coefficients. What the Cn will give me? Okay, so this is simply the probability amplitude. Okay, or in other words, the mod of Cn square will give me the probability amplitude that the particle is being found in state n. Clear? Okay. So let's take our state. So we also have this kind of state psi of t that is related to this phi of t. If you see, this phi of t is a state defined in the interaction picture. Okay, so I'll use for the time being this kind of notation, then I'll switch over the notation to different kind. Okay, writing that explicitly. And psi of t was an eigenket where, it was a state vector defined in the Schrodinger picture. Clear? Or in the Heisenberg picture. Clear? So how we wrote that, if you remember, so yesterday we put this phi of t like this in e raised for I h naught t by h cross acting on this psi of t. Got it? So I'll write it like this thing now. The psi of t I can write e raised for I minus I h naught acting on this phi of t. Okay? So now what is our phi of t in the eigenbasis? So it's like this thing. So it is e raised for minus I h not by H cross, summation over n, C n T, okay, n. Okay, since n is the eigenstate of what? H naught. So I can take this as an operator, it will act on this eigenstate. So you are having e raised power minus I H naught T by H cross acting on n. Clear? So what it will give me? So this is an operator, it will act on this n, it will give me the eigenvalue of n. Clear? Corresponding to n. So it will be simply C n T e raised power minus I E n T by H cross acting on n. Clear? So this is how we can write this psi of t in terms of this expansion. Okay? So let's assume, so let's assume our V, we don't have the perturbation. This Vi of t is 0. Okay? So assume this Vi of t is what? So there is no time dependent part in our Hamiltonian. So what does that mean? So if Vi of t is 0, so that means this side is 0. Clear? It means this phi of t is a constant quantity. Clear? It's a constant wave function. That means it does not evolve in time. It remains constant in time. Clear? So if this happens, it implies this phi of t is what? Constant in time. Clear? So if phi of t is constant in time, so what happens to, what about this thing? This Cn. So Cn, if phi is constant in time, then what about this? Cn has to be constant in time. Clear? So which implies therefore the Cn t is equal to simply Cn, that is constant in time. Clear? So there is no time dependence. Now let's look at this. So this psi of t, time dependent wave function, that is defined in the Schrodinger picture. Okay, so that is the same thing, summation of n Cn e raised power minus I E n t by H cross n. Clear? So this is the well-known result of the expansion, the figuring out the time dependence of a wave function in terms of the stationary eigenstates. Clear? You remember this result, eh? So you can write like this thing, okay? Psi of x t equal to 0, let's say, some vector, some space dependence. It is not necessarily the coordinate. Oh, sorry, it is a coordinate. Space dependence I will take. So it will be simply summation of C n when I put t equal to 0. This is the well-known result. So that means this expansion is valid for us. Okay? Yes, sir. Got it? Okay, so now we have shown this expansion is a valid expansion. Okay, it reduces to the well-known results, what we know from the time-independent Schrodinger equation. So now we substitute this equation, this phi of t here. Okay? Okay, so let us substitute this equation. Okay, so let me call this as 1, call this as second, using equation second and equation 1. So what does that mean? So it is I H cross partial by partial t. Okay? Yes, so you are having summation of, I will put summation of m. Okay, because n is a dummy variable. Okay, so it is C m of t, like this thing. So I will write like this thing, b I tilde of t, summation of m C n of t. Okay, got it? Like this. Clear? So what is our goal? To figure out what the Cn is unknown to us. So that's why we are plugging that equation 2 in equation first to get the value of the Cn. Okay, the C. If we know C, we know the probability. Is it? Got it? Okay. So this I can write as or I H cross. So you take this out. Okay, so d by dt of this thing, I will put a dot, summation of m. So it is C dot mt m. So that's equal. So let me put a completeness condition M. So M like this thing, V tilde I of T, okay, summation of N, Cn of T. Okay?
Yes, sir.
So what it is here? So you can write it as summation of M, summation of N. Okay, so this objective, so you are having this M, V tilde I of T, okay, and then you are having this Cn of T, then you are having this N. So this is a statement and I put it at the end. Rest are the scalar quantities. Got it? Okay, so you are having, so summation over M this thing. Okay, so these are terms are linearly independent. You can compare the coefficients. That means I cross C dot M is equal to summation of N this object. Got it? So let me write carefully. So you can write it as like this: I summation over M, like this thing, C dot M of T, okay, minus summation over N, okay, M V tilde I of T, okay, N, then you are in C N of T, okay, this get is equal to 0. Got it?
Yes.
Since all these are linearly independent, it means this coefficient must be equal to 0. Okay? So it means this thing. So it means we are having this equation. Got it? So I remove the summation.
Yes, sir.
Okay. So what it means? Now look here. So you are having for every m, is it? Let's take m equal to 1. Got it? But there is a summation over n, is it? Is that true? How many terms are there? So let's say if you are having m equal to 1, m equal to 1, summation goes, it can go 1, 2 and so on. How many, the number of states available, clear? So that means it's a couplet differential equation. So how many couplet differential equations are there? M number of differential equations. Got it? If you see, it's actually a matrix equation.
Yes, sir.
Okay. So now it's very complicated to solve. Although it's a linear first order differential equation, you are having only the first time derivative, but all these equations are coupled with each other. Let's take m equal to 1. So the first equation will depend on all other coefficients. If you are trying to figure out the first coefficient m equal to 1, it will depend on C1, C2, C3 up to C. Clear? So it will be coupled with all other levels. Got it? So we need to figure out the approximate method to calculate this kind of equation. Got it? So let's simplify it a bit. So I can write it like this way: IH cross d by dt of, okay, let me write on, so we should put a partial, okay, so I'll write like this: C1 of t dash 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 Cm of t. Clear? So these are all the coefficients. Then I will write it this way. Anybody? Can you tell me what this is? So it will be 1. Okay. V tilde. Okay, then 1. Clear?
Yes,
Then 1 V tilde I T. Okay. 2. Dash, dash, dash. Okay. 1 V tilde I T. Okay. So let's start. Okay, m number of equations. Got it? So similarly, you are having all these. So you are having m. So we are going. We are having m number of equations. Got it? So you are having C1. So you can put it in a more beautiful form. So let's write this m v tilde I t n. So you can put it in this form. So m, what is this thing? It is e raised power I Okay, H naught T by H cross. Then you are having this V I of T e raised to power minus I H naught T by H cross. Clear? So this is the representation in the interaction picture. So this is the eigenstate of this H naught. It will give me I E M T by H cross. So this is also the eigenstate of this H naught. So it will give me e raised to power minus I E N T by H cross. What remains? M V I T. Okay. So what is that equal to? So I will put it as E omega M N T. So let's write this as V M N T, where this omega M N is equal to E M minus E N, usually known as the Bohr frequencies. Okay, and V M N T, these are the matrix elements of this time dependent potential or the perturbation in the eigenbasis of this H naught. Got it? Okay, so I can rewrite this equation as like this way. So you can put it this equation as C dot MT is equal to summation over n e raised to power I omega M N T. Okay, then you are having simply V M N T C N. Okay, so let's take an example. Any question?
Sir,
Yes.
sir, how could we physically, comprehend this coupled with other states?
Yes. Suppose if you are having a time dependent field, clear? So you take think of many levels. Let's say you are having let's consider first only two levels. That is the example what I am going to show. Okay. So let's take level 1 and level 2. Clear?
Yes, sir.
So if you are having a time dependent field, so this there is a possibility that this electron, let's assume there is an electron, clear? There is a possibility this electron may get a transition to this very state. Clear?
Yes, sir.
Okay, so when there is a transition between the two states, in this way they get coupled. Clear? So it means, so if you are having an n levels, let's say I am taking only the discrete case, if you are having n levels, so that means there is a possibility that the electron makes transitions to, or this particle can make transition to all these very states. Clear? So it means there is a finite probability of figuring out the particle either in this state or any other states. Okay, so in this state they are coupled. So this gives me that kind of notion.
Yes, sir.
Okay, so you are having, even though you are getting the dynamics of the particle in the only one state, it does not remain there only. It makes jumps to all other states. Got it? Okay, so in other words, there is a finite probability of figuring out particle the other states as well. Got it?
Yes, sir.
Okay, so we are going to take this example, then you can understand it, what is happening. So let's take the two-level system, our favorite system. Subjected to time dependent perturbation. Okay, so let's write the Hamiltonian for our two-level system, that is H naught. Okay, so let's write H naught. So I will write, let's say E1. So it is the energy of the of the level 1. Then you are having E2 level 2. So what I am considering, I am having a two-level system. One is level 1, another is level 2. So let's write E1 as the energy of the one level, energy of the level 2. So it means I am considering E1 is less than E2. So that is, I can say level 1 is the ground state. And this is the first exit. This is the exit state. Because there are only two levels, you are having this kind of. So you are having, this is our what? No, this is only our two-level system. Clear? So what are the eigenstates here? So you are having only two eigenstates. So H naught So it gives me E11, and then you are having H0 acting on 2, giving you E2. So there are only 2 eigenstates, and that's why we call it as a 2-level system. Okay, so now let's add the perturbation. So let me write this V of t to be some, let's call gamma as the amplitude of, okay, so are the strength of the perturbation. In terms of these exponential factors, okay, are the oscillating, I'm applying the oscillating field like this thing. Okay, so these are simply the off-diagonal terms of the matrix. Clear? So what it means, so I am applying, so this is V of t, so it means this kind of object means there is a transition between level to 1 and 2, and this means there is a transition between 2 and 1. Got it? Okay, so if you write it in the matrix form, it's like this thing: 0, gamma e raised for I omega t, gamma e raised for minus I omega t, 0. Clear? If you write it in the matrix form. Samajh? Okay. So now if you see what are the diagonal terms of this V, they are 0. There are only off diagonal terms. That means 2 levels are coupled by this very perturbation. Okay. So you can think, so this is the same kind of experiment you are doing, the ESR problem. Clear? Okay. So what you are doing? So you are applying the external field, a harmonic field, a sinusoidal field. Okay, what happens to the spin? It flips the state. It goes from, let's say, down state to the up state, and up state to the down state. And you are getting what kind of peaks? So you are getting absorption and emission. Clear? Got my sinusoidal peaks. Is that true? So we'll see that kind of phenomena happening. So this is the model for that kind of problem, what you are doing. Okay? Okay. So now let's look at this kind of equation. We need to solve this equation. Clear? Okay. So let me write it. What I need to calculate this Vm of t. Clear? Okay. So let's write first. Okay. So you are having how many levels? Let's look at the level 1. M is equal to 1, M equal to 2 in this very equation. So you are having this thing, C dot 1 of t. So that's equal to, okay, summation over n. There will be 2 these things. What will be there? N will be only from 1 to 2. Okay. So that will be e raised for, since M is equal to 1, it is e raised for omega 1 1 t V 1 1 t C 1 t plus, then you will have e raised for I omega, M is 1, N will be 2, then V 1 2 t, then you are having C2. Clear? Then now let's write this I trust for the M equal to 2. So it will be, okay, so it will be e raised for I omega 2 1 t V 2 1 t C, okay, 1 t plus e raised for I omega 1 1, sorry, 2 t V 2 2 t C2. Clear? So this is the set of 2 equations. They are coupled. Clear? So now let's check what this V11 is. Okay, so let's, everybody followed it? Okay. Okay. So what is V11? Now look at that way. So V11 of t means like this thing, 1, V of t and 1. Clear? So if you look at the matrix elements, you are having 1 on this side, 1 on this side, and 1, 2 are orthogonal to each other. Clear? So that's equal to 0. Similarly, that's equal to V2 to t. Got it? Samajha? Okay. So that means this term, it is equal to 0. This term is equal to 0. Okay. So now let's look at this V12. Okay. So let's write this V12 of t. So what is that? 1 V of t and 2. So how much is that? So 1 and 2, it means this very term. So it is gamma e raised for I omega t. Okay, so that is simply equal to V21 t, it is star. Okay, if I calculate V21, that will be actually e raised for minus I omega t. That is the star of this. Okay, so let's define Okay, so define omega naught is equal to omega 1 2. So what is omega 1 2? Omega 1 2 is E1 minus E2 divided by H plus. Clear? Samajh? So that's actually equal to minus omega 2 1. So 2 1 will be simply minus. Got it? Everybody?
Yes, sir.
Okay. So so we'll write, therefore we are having IH cross C dot 1 T, that's simply equal to, okay, e raised for I omega, so that will be omega naught, and there is this gamma, okay, so it will be simply gamma e raised for, I think there is a sign problem. Okay, so I will put it this way. I will write it as okay, like this. Let me write this thing 2 1. So it is 2 1. Okay, so that's minus 1. I will define omega naught to be omega 2 1. Okay. So this will be simply e raised for I. Okay, it will be minus omega naught. So it is simply omega minus omega naught t, then you are having C2t, and you are having I h cross C dot 2, so it's equal to gamma e raised for minus I omega minus omega naught t C1t. So these are two Kepler differential equations. Clear? So can you solve it? So they are very simple to solve. Okay, so let me give. Okay, so I will just simplify them a little bit, then you proceed yourself. So what I will do, I will simply remove this exponential factor here. Okay, so for that matter, what I will do, okay, yes, there is one important point which I forgot to mention. The Kepler differential equation, what we got. So when you solve a differential equation for a given problem, the initial conditions must be set. Clear? So we have arrived at two Kepler differential equations, is it? So, but we have not set any initial condition yet. Got it? Okay, so what is the initial condition I will set? Okay, so I will assume an initial condition. Because without any condition, you can't solve a physical problem. You can solve a problem arbitrarily, but without any kind of conditions. Clear? But when you do a physical problem, you need to set the initial conditions. Clear? So what I will do, since I am having a two-level system, okay. So what I will assume, okay, so mod of C1 square, it will give me the probability here, and mod of C2 square will give me probability in the state 2. Clear?
Yes,
so what I will assume only the ground state is populated initially at t equal to 0. Initial condition means at t equal to 0. So my C1 is equal to 1. That means particle is having 100% probability where? In the level 1, and there is no probability of finding the particle in the level 2. Clear? Got it?
yes, sir.
So or I can write it this way. Okay. So let me write it as C at t equal to 0 is equal to 1. C at t equal to 0 is equal to 0. So that means only the ground state is populated and the excited state is not populated. There is no population at all in the excited state. Clear? Okay. So subjected to this very initial condition, let me simplify this very equation. Okay, you can put this simple equation in Mathematica. That will give you the solution. But so let me simplify it for you people little bit. Then you proceed on. Okay. So let me define. Okay. So let's define this. Let me write C1 of t as some A1 of t. Let's write A of t e raised for I omega minus omega naught t by 2. Clear? And C2, so I will transform this into these variables a n minus omega naught t by 2. So what will be the initial condition in terms of a? So I am simply transforming it into new variables. Okay, so what will be the initial condition? So if A of 0 is equal to 1, B of 0 is equal to 0. Clear?
Yes, sir.
Okay, so once you do, okay, so one more point. So you are having initial, okay, so conservation of probability is always there. Eh? So what is the conservation of probability? Mod of C1 square plus mod of C2 square. That should be actually, that should hold at any time. Eh? Okay, so this is very important point. The conservation should hold at any time. Okay, got it? So if you start initially, conservation of the probabilities, it should hold any time. So at any time, it means there is a finite probability here as well as here. Clear? Or it may happen, it will go, particle will entirely go here, there is nothing here. Got it? Okay. So it means, so this A of P mod of A of mod of this thing plus mod square this thing plus mod square this thing is simply mod square of this thing, mod square of B square. So that's equal to 1. So you should remember these things. So once you do it, so just plug it there. So what you will get? Okay, so you will get this set of equation I H cross, and again some lengthy thing. Sorry. A is equal to gamma B. Okay. Then you are having I H cross B dot. This will be H cross omega minus omega 2. So it will be B is equal to gamma E. Okay. So now if you see the first equation, let's look at first equation. So you can see this B acts as a source for A, is it? And here in the second equation, A acts as a source for B. Clear? Okay. So let's do one more simplification. Okay. Okay. So what I will do now, I will use, okay, so I want to remove this time dependence. Okay, so there is another method to do it, simply by Laplace transforms. So you convert it into a second order differential equation in C1 or C2, clear? Got it? So you just differentiate it. Okay, so what I want to you, just differentiate this thing. What you will get? You will get C dot 2 here. So C dot is actually equal to C1, clear? So you will be having a second order differential equation, and you will be able to solve this by simply the Laplace transforms. Got it? So that is the thing, but I am doing it in a rough way here. Eh? I am giving you some different idea how to solve it. Eh? Okay, because these kind of equations often occur in physics. Eh? Okay, so what I will do now, okay, so let's use this thing. So let me write this A equal to some A0 e raised power I omega t, and B equal to some B0 e raised power I omega t. Okay, where A0 and B0 are constant. A0, B0 are constant, and omega is unknown. This omega is unknown, and we need to figure out omega. Clear? So what I am doing, I am actually removing the time dependence, this A. So it is simply what I am, when you remove the time dependence, it is some sort of, you are doing a Fourier transform in time, in T domain. Eh? Clear? Okay. So if you see, it is some sort of Fourier transform, although it's not exactly the Fourier transform, because Fourier transform will involve an integration. Clear? Got it? So I'm simply making this kind of extension, and I will try to figure out this omega. Clear? If I know this omega first, okay, so what kind of values of this omega are available, then I can fix this A and B. Clear? Got it? Okay. So then I can actually know this A naught and B naught. If I know A naught and B naught, I will be able to figure out A and B. Got it? Okay. So let's substitute this here. So you will be getting like this in H cross omega plus omega minus omega naught by 2. So you'll be getting A naught plus gamma B naught is equal to 0, and you are having gamma A naught plus H cross omega minus omega naught by 2 B naught is equal to 0. So you have got now the set of two algebraic equations. Just you have to substitute. Okay, let's substitute. A, when you substitute, this is a constant, So I omega will come down. I omega will come down. What you will get? Minus, is it?
Yes.
So extras. So I have put extras out and I have taken actually this minus out. Clear? So what you are having? Extras omega. That omega and plus this omega minus omega naught by 2. So when you put it here, since you have taken minus out, that you keep here and you put it here, it will be plus. Got it? Okay, so this is how it is to be done. Now, so what, this is an equation unknown is A naught and B naught, is it?
Yes, sir.
When the possible solution is there. So now this is an algebraic equation, clear? When is the possible solution? When the determinant of the coefficients is 0. So when the determinant of the coefficient vanishes, then I am having a non-zero solution for A naught and B naught, clear? So you can put it like this thing. So I can write it, okay. So a non-vanishing, a non-trivial solution for A naught and B naught means determinant of coefficient matrix vanish. Clear? So now let's look at the coefficient matrix. So let's look at that determinant. What is that? So it's omega plus omega naught minus 2. Then you are having gamma here. Okay, there is an extras also, like this thing. So you are having gamma here. Then you are having extras omega minus omega minus omega. And this has to be equal to 0. So just multiply it. Okay, so you will be getting the solution. So a non-zero solution exists, non-vanishing solution exists for omega is equal to plus minus. Okay, or in other words, omega square you can write. Okay, so omega is equal like this thing. Gamma by h cross whole square plus omega minus omega naught by 2 whole square. Clear? So now look at, just you need to work out that determinant. So what you are getting? Okay, so if you are not able to figure it out, so you are getting h cross square, omega square minus this square. Clear? Minus gamma square equal to 0. You need to figure out only omega square. That means you take this on the other side, it will be plus, and take this also on the other side, it will be plus, and divide it by h cross. Got it? Okay. So this is the solution. So now you are having two possible solutions. Okay. So it is because you are having two solutions. A and B are the these numbers we need to figure out are the functions. Clear? So now therefore I can write the solution A of t. Instead of writing A naught now, I will put what? A of t. So it will be simply some unknown constant e raised for I omega t plus some beta e raised for minus I. Clear?
Yes, sir.
Teacher?
Yes, sir.
Is it? This is the solution because where from it comes? So it's you are having a coupler differential equation. That's why you are having two constants. Two coupler differential equations give you two constants. In other words, if you put it only in terms of A, then you will be having a second order differential equation A. That's why you put what? Two constants here. Clear? But they are coupled, is it? Is that true? So if I write now B of t, now tell me, if I write now B of t, what should be the form of B of t? What should be the B of t should be consistent with these two equations. Because if I know A, let's substitute A here. I have to obtain B from this equation. I cannot randomly put B. Clear? So that means these exponential factors will be there. And these coefficients alpha and beta will be also there in addition to something more. Okay? So you put A dot here. So it will be I omega alpha kind of thing. Then you put A, color the terms. Okay, and you will figure out what? B. In other words, I can write this B of t like this thing. Let me write some R alpha, alpha e raised for I omega t plus some R beta, beta e raised for minus I omega t. Where these coefficients need to fix out from where? You plug this B in the other equation and see and compare with A. Clear? You will be able to figure out these R alpha and R beta. Got it?
Yes, sir.
So that is the assignment. Okay, so you this R alpha turns out to be omega plus omega minus omega naught by 2 divided by gamma by h cross, and this R beta. So there are actually two possibilities of these things. Clear? So this is something. Okay. Now we will apply the boundary conditions. Okay, we have got A of t. We'll be getting what? If we know A of t and B of t, what we'll get? C of t. C1 and C2 we are written in terms of A and B. Clear? Okay, so now let's apply the boundary conditions. Okay. So let's apply the boundary condition or the initial conditions, I should say. So what is the initial condition? Okay, A of 0 is equal to 1. So what is that? So it means alpha plus beta. Clear? Got it? Okay. Or okay, let me write it this way. A of 0 will be simply alpha plus beta, that's equal to 1. And B of 0 is actually 0. That means R alpha alpha plus R beta beta is equal to 0. So let's calculate now. Okay. So what it means? R alpha alpha is equal to minus R beta beta. Clear?
Yes, sir.
So let's use it in B of t. समझ आओ?
Yes, sir.
So let's use it in B of t. So therefore I can write B of t is equal to, so you can put this R beta beta as minus times. So you can take this out, R alpha alpha, it will be simply e raised for I omega t minus e raised for minus I omega t. Clear? समझ आओ? So this is alpha. Okay, we need to figure out alpha from here. You need to solve these two equations, you will get alpha. So समझ आओ? Okay. So because I have put only in terms of what? Alpha. So what it will be? Twice I R alpha alpha sine of omega t. Okay? Solve for alpha here. Okay? Solve for alpha and use that here. And use R alpha here. What you will get ultimately, you will get this B of t like this thing. Okay? You will get something gamma minus I gamma by h cross omega. Okay? And then you are in sine of omega t. Clear? समझ आया? So what is B of t? Okay. So let's write it. So everybody followed it?
Yes, sir.
So these are trivial things, you need to do it. Huh? Okay. So we are having, therefore I can write this C2 of t. So that's actually B of t e raised for minus I omega minus omega naught t. Clear? So what C of 2 gives me? Amplitude. समझ आया? But what I am interested in calculating the probabilities. So therefore, okay, probability of figuring out the particle in the state 2, that is C of 2 square. What is that? Simply mod of B of t square. Mod of this is 1.
Yes, sir.
So what that will be? Simply mod of I is equal to 1. Clear? Okay, so it is simply gamma square. Let me put it like this in h cross square divided by omega square. That is something gamma square by h cross square plus omega minus omega naught whole square by h cross square sine square. Okay, omega t. So that is simple. Okay, let me put this omega gamma square by h cross square plus omega minus omega naught square. Sorry, not h, it is 4 by 4 raised power half into t. Clear? समझ आओ? Or you can simply put gamma square by omega square h cross square sine square omega t. Clear? So what is there for the C1 of, you don't need to calculate C1 from there. C1 you will simply calculate from this thing, from the normalization condition. Got it? समझ आओ? So we need to interpret this result. What is happening? Okay? समझ आओ? Okay. Okay, so if you see the probability is oscillating, it's oscillating in time. Okay, so this is very important point. Okay, so what is the oscillation frequency? It's omega. So omega will give you simply the oscillation frequency. Clear? So there is no problem. Okay, so we'll be having the, okay, so let's okay, let's look at the when the okay, so it will be like this thing, sine square. So I'll it is on without any so it is on the free axis. So you will be having something like this thing. Clear? So let's say if this is C1, initially we started with the maximum population, is it? So when it is oscillating, so look here, initially C2 is 0. So you are having maximum probability, clear? But what will happen? So as time goes, so this will decrease. So that's happening here. Now what will increase? C2. So it means this will increase in the sinusoidal fashion like this. Okay? So you call this as C2. So once this is minimum and you will be having this as a maximum, and once this is maximum and you will be having minimum kind of thing. So these are the oscillations, okay, that the probabilities can make. So that means you can figure out the particle makes oscillations between the two states. Okay,
Yes, sir.
these oscillations are in general known as Rabi oscillations. Okay, so we call them as Rabi oscillations. These are very important, these kind of oscillations. Okay, so now let's try to understand. Let's look at what is the maximum amplitude this can go. Okay, so what is the maximum amplitude? Maximum amplitude will occur when omega is equal to omega 0. Clear? So when you are having omega equal to omega 0, so when omega is equal to omega 0, we call this as resonance condition. Okay, so that means the external frequency is set at the natural frequency, the width of the levels. That is what you are doing in the ESR experiment. Clear? Okay, so you will be having the maximum peak now. Okay, so what will be the maximum? So this will, okay, it will be like this. So let's say you are having at 0 here, okay, and this is 1 here. Okay, so initially particle is where? Particle is in the state 1. So that means you will be having like this thing. So I am not clear.
Yes.
So it will go to 0. So this is your mod of C1 T square. So it's not a broad, it is something. So you understand, right? Okay, so at what level it, okay, so what will happen now? So that means what is happening? Okay, so look here. So you are applying the external perturbation. The particle is initially here, and okay, it is initially here. Now it moves to where? This state. So it means the system is absorbing energy from the field, is it?
Yes, sir.
So that means the external potential, the external field, what we are applying, will act as a source of energy here. Clear? So it will be absorbed by the particle here, and it will go here. Or you can say the state here, it will go now, it will flip the state, clear? By absorbing this much of energy. So that means this will increase. So you are having C2 of square here. Maximum value, huh?
Yes, sir.
Okay. Now what will happen? So this will now lose energy, clear? And this will gain energy.
Yes, sir.
Got it? Okay, so that means this will just emit that much of energy. So once it emits the energy, where it will go?
State.
So the particle will go to state 1, is it? In this case, the external field will act as a sink. Clear?
Yes, sir.
So that means the external potential of the external time dependent field will act as the source and sink for these transition to happen. Got it?
Yes, sir.
Samajh? Okay. So anything more? Okay, and these oscillations can occur for away from the resonance condition as well. Okay, so we are looking at the maximum, huh?
Yes,
But if you are away from the resonance condition, it is not necessary. You will start from 1 here and this will go to 0. It will go to some finite value, and it will start from finite value here. Clear? If you are away from the resonance condition. Clear?
Yes, sir.
Okay. So what is this value while it will go to 0? So what is this value?
Gamma square.
Since we are at the resonance condition, what will happen? So this omega is simply gamma by h cross. So what is the time here? Since we are on the time axis, so it is on the time axis. What will be the time? Huh?
इसमें put करेंगे 0 यहाँ करेंगे h cut by sin
What will be the time?
sin inverse h cut gamma.
Huh? Yes. By h cross by gamma.
Sin
Okay. So what will be
inverse
this very point? 2 pi. 2 pi h cross by gamma. Gamma. Clear? So these are the values. Because if you substitute this pi h cross, where in this very case, in this situation at the resonance, it will be what? Mod of C2 square will be simply equal to gamma square. It will be simply equal to sine square. Okay. Omega will be gamma by h cross. Clear?
Yes, sir.
So that means
C2 is
it should be equal to pi. This object should be equal to pi. Clear?
Yes, sir.
So that's what you are doing here. Multiplies of pi. Even multiplies of pi. Okay.
Yes, sir.
Sorry, simply multiplies of pi. Okay. Clear? Okay. So let's move. So how much time is remaining?
10:26.
10:26 was it?
Yes, sir.
Let's stop it.